Thanks to Ross for the invitation to come back a second time. This is the main talk that we really wanted to talk about. The other one was Ross's request. So Creutz-Taube published in 1969, got Taube the Nobel Prize. Professor Hush was intricately related with the work both before and after the molecule was published and its interpretation. It was the first time a system had ever been produced which showed delocalized electrons over large distances. And this molecule was the classic paradigm to understand photosynthesis. All the 80s papers referred to it to try and understand photosynthesis, and every grant that's ever been written to work on the Creutz-Taube ion said that it's the classic model of photosynthesis. Now, photosynthesis we understand, the Creutz-Taube ion we still don't understand. So now we're using photosynthesis, what's been developed, all the stuff in the previous talk, to try and understand the Creutz-Taube ion. And the work was Brett Wallace. That's a postdoc who did a lot of the work. And I guess we'd like to thank the ARC and APAC who put up the money for the project. An overview. First I'll tell you about the Creutz-Taube ion and what it is, but then we go on from that, we'll do classical simulations of the relaxation of the Creutz-Taube ion in the excited state using classical MD simulations, and we'll calculate the Stokes shift function that's appeared at this seminar, this conference a lot. Then we'll transform that into the spectral density, and then we'll introduce discrete mode approximations to the spectral density, which allows us to connect to everything that we saw in the previous talk, where we had 70 vibrational modes. They were all modes of the chlorophylls. Now we'll take discrete vibrational modes to represent the solvent, and we'll try and do the same task. Then we do the full quantum dynamics of the system with this restricted number of modes. And there's a lot of effects we're trying to understand on the Creutz-Taube ion, and so the solvent and the internal effects get mixed together and when we try and understand the properties. But the last slide is when I did one thing too many, which really says that a large amount of what comes before is a load of nonsense. And now we've never published a single paper with a spectral density or anything like that in it before, so we're right out on a limb here. And we've gone to the extent of where the methods that we used in photosynthesis are no longer adequate to describe the problem. And I guess that's what this conference is all about. Paul Ross came to Sydney on last Thursday, and this seminar lasted 3 hours on Thursday. Now, a key bit about what we're looking at here. No solvent, no transition. The solvent is not gently perturbing what's going on. The solvent is what's going on. And that's a fundamental difference to everything we've seen previously at this conference. And so some of the equations are interpreted differently. And I don't know if that interpretation is valid. No one's ever done it before. But that's the reason why. So, the introduction. The Creutz-Taube ion is there's two rutheniums here. Remember the periodic table, it's iron, ruthenium, osmium. So ruthenium is like iron, it can be ferric or ferrous, 2+ or 3+. And there's 5 ammonias around each side here, A for ammonia. And sitting in the middle is pyrazine. And the whole molecule is given a 5+ charge. So 5+. What happens to the 5+? Do you get 2+ on one side and 3+ on the other? That's a charged localized situation. Or do you get ruthenium 2.5, ruthenium 2.5, which would give you an effective covalent bond between the two rutheniums, as if the pyrazine in the middle didn't exist. This was the first molecule ever produced that wasn't clearly charged localized. And that's why it was such an important thing and why it got the Nobel Prize and why it's the paradigm for photosynthesis and many other forms of charge conduction. So the question that's in trance for 40 years, localized or delocalized? To understand the question, there are a few basic concepts. I think most people here are probably familiar with them. The reorganization energy lambda is the key one. That's how much energy is lost when you go from one form to the other. And that can be manifest in three different ways, of which the only way I'm going to talk about in this seminar is the antisymmetric solvent vibrations. In the previous talk we talked about the antisymmetric intermolecular vibrations only. Here we're going to talk about the solvent vibrations. And then there's the electronic coupling J, which acts between the two ruthenium d orbitals. And one thing Professor Hush showed early on, the ratio of 2J to lambda is the critical thing. If 2J is greater than lambda, then in the middle here, the charges are fully delocalized. You've got ruthenium 2.5, ruthenium 2.5. But if 2J is much less than lambda, then it's a fully localized system. The charge is trapped on one side. But the intermediate regime is when 2J on lambda is approximately equal to 1. And it's quite clear now that that's the scenario that's appropriate for the Creutz-Taube ion. The mutants of the reaction center we saw previously allowed you to tune nicely across all these regions. So that's why the system is very beautiful and controllable. But here, not such great control. And the debate raged for 30 years on whether it was localized or delocalized. Professor Hush led the charge to say it was delocalized. And after about 25 years, there was a paper published containing 30 authors. All the authors were the people who've been taking the opposite view. And so the paper was called the Creutz-Taube ion Revisited, and their conclusion was it's delocalized. So the evidence to support that was pretty clear from the beginning. The X-ray structure is nearly symmetric. You don't have different bond lengths on either side. But that could be a furphy because the X-ray structure could just be a time average of two localized structures. And the inner valence band, the band that we looked at before in the reaction center, just like the reaction center, was very sharp. It's got a long tail. That's the classic shape of a delocalized transition. A localized transition will be 4 times broader. They'll look Gaussian in shape. A localized transition will be solvent sensitive because there's a huge dipole moment when the electron moves from ruthenium 3 on one side, so ruthenium 2 on one side over to the ruthenium 3. There's a change of dipole moment of 30 dBs, something like that. So it's a huge solvent interaction, huge solvent sensitivity. The Creutz-Taube ion is completely insensitive to solvent. Doesn't matter what solvent you use, the spectrum's the same. Now, if it was localized, like ammonia is localized, a localized structure with a pyramid, but in the microwave region you can do the tunneling transition from one pyramid to the other. If this transition was localized, there'd be the tunneling transition. You could pick it up. People searched for it for decades, they never found it. Thomas Krauss in Canberra, one of the leading players in that. And finally, Steve Boxer measured the Stark spectrum. And the Stark spectrum shows 0 dipole moment change from the ground to the excited state, indicating a completely delocalized system. There is no more authoritative experiment than the Stark spectrum. So why is this topic back on the agenda again? Well, it's a matter of time scale. This experiment is very slow, therefore it's not particularly useful. But the Stark experiment here and the band shape experiments here, those experiments are over within 10 to 20 femtoseconds of the light excitation. So anything in the dynamics that happens after that period of time does not change the band shape or change the Stark spectrum. So these experiments are telling you the very, very short initial dynamics, and there is no doubt that the Creutz-Taube ion is delocalized on a femtosecond timescale. But traditionally that was the only question that was of interest because this is a slow experiment, you don't know how to interpret it, but if you can do the fast experiment, down here, then it's all over. There's no more discussion. But it's that paradigm that's been reversed in the last few years, that the fastest experiment is the one that's the most valued. And the one in the middle I didn't mention. The ruthenium ammonia stretch frequency, that's a spectator. It doesn't take part in the charge transfer process. It sits there and it looks at it. And it tells you what's happening with the charge transfer. So you only get a single ruthenium nitrogen stretch frequency. And this is the data from a paper of Professor Hush's in the early 70s. If you make a 4+ system where there's ruthenium-2 unambiguously, the stretch is at 438 wave numbers. You make a 6+ system, the stretch is 461 wave numbers. If the system was charge localized, and there are very many molecules that have been made that are charge localized, this is a well-known paradigm, you see two lines, 438 and 461, are both seen in the infrared spectrum. What do you see for the Creutz-Taube ion? One line at 449. Right in the middle. If it's delocalized, you expect to see one line at the geometric mean of the two localized frequencies. So that's what you see. This is a picosecond timescale experiment now. You're getting 10 wave number resolution. 10 wave numbers is 3 picoseconds. So you're doing an experiment which is lasting on the order of tens of picoseconds. Anything that the molecule does within tens of picoseconds will be manifest in that vibration frequency. So it's a longer timescale experiment than the Stark measurement, but a very much shorter experiment than the X-ray. Now, the cat amongst the pigeons has come in the last few years with some experiments on the same timescale, the picosecond timescale, which have come up with the alternate conclusion. And in particular, this is infrared spectroscopy now with the pyrazine modes, not the ruthenium ammonia modes, but the pyrazine modes in the middle. You see, in the infrared, you see Gerarda motions of the pyrazine, which are forbidden in pyrazine itself, but they appear in the infrared spectrum of the Creutz-Taube ion. And similarly, antisymmetric vibrations of pyrazine appear in the Raman spectrum of the Creutz-Taube ion. So if it really had a centre of symmetry, both of these things couldn't happen. So these are picosecond timescale experiments which says the charge is localized, because if the charge is localized, there's no Gerarda, Gerarda anymore. You've broken those symmetry operators. All transitions are allowed. Tom Meyer has been the person who's really pushed this. A major review in 2001 has come back and said, no, the problem is not solved. There are these real experiments that are not yet to be answered. So we're trying to answer them. And so to do that, we've tried to look at the motion of the solvent around the Creutz-Taube ion. So here's the Creutz-Taube ion in the middle, and we put 200 water molecules in a shell around it. This is a cluster, because the software I was using couldn't do periodic imaging, and I had 2 days to do this. We run thermal ensemble calculations at 298 Kelvin on this cluster using the amber force field. The parameters for that we developed ourselves in the mid-90s, where we looked at the solvent effect of this type of class of molecules. So it's really easy to generate the amber force field for an arbitrary molecule like the Creutz-Taube ion. And it's reasonably good. So once we run the molecular dynamics on the ground state of the system, and here the Creutz-Taube ion in the middle here is rigid. We're not looking at any property of the Creutz-Taube ion's vibrations. We're only looking at the solvent interaction. And we're trying to calculate the reorganization energy, the term that drives charge localization. So in this, we've ignored the electronic coupling. We've assumed it's zero, assuming it's a fully charged localized system, what would its spectrum be? What would the time response be to that? And that is the input that goes into the calculation which deals with the delocalization.
So you mean you actually put a 2 plus and 3 plus on?
Yes.
Okay.
Fixed charges of 2 plus and 3 plus. There is no interaction with the excited state and curve crossing. Just a ground state simulation. Very, very simple, straightforward. And so then we sample initial conditions out of that molecular dynamics trajectory, and then excite those initial conditions to go to the excited state, and now we look at the dissipation of the energy when you've gone to the excited state as the system tries to relax back. Radio. It starts at 1. This is your Stokes shift function, but it's now the solvent solute energy. It's not the it's not the chromophore energy anymore. The chromophore has no energy. It's the solvent solute energy that's driving everything. And it very quickly decays here as you see the vibrational motions pick up amplitude. This decay coming down here looks very much like everything else that's been presented at this conference for plasma relaxation and water. And in fact, it's very close to what was measured by Barber and Hupp for this similar system here with the cyano group, which places the Creutz-Taube ion. And you see long time fluctuations. So from that we can Fourier transform it and get the spectral density, but this is the spectral density over omega, which is actually d lambda d omega. So it's the distribution function of the reorganization energy. And most significantly, there's a zero frequency response sitting here, and that's what goes wrong with all our normal methods of dealing with it, the zero frequency term. 19 wave number peak, classical of water response. 71 wave number peak, also classical of water response. But the most significant feature in water, which gives it its relaxation time, is 180 wave number hindered translation. It's not present. These hindered translations are not coupled to the electron transfer process. The only thing that's coupled is the libration out here. The water molecules are trying to rotate, to reorientate from pointing at one ruthenium to pointing at the other. And that's where all the coupling is. Integrate that curve and you get the reorganization energy as a function of frequency, ending up at about 7,000 wave numbers, which is about right. But it's now distributed into various modes. So we wanted a discrete mode representation to represent this function. And so to do that, we divided it into 3 regions: a low frequency region, a vibration region, and something in the middle region, each of which took a large amount of the reorganization energy. And then this gives us a 3-mode model that we plug back into our quantum equations, and then we're off doing exactly what we did for the reaction center. This just says that 7,000 wave numbers for the total reorganization energy is about right. If you take this class of molecules here and do calculations for them, you get those 3 values, which is very close to experiment. Linearly project down to the Creutz-Taube ion calculated value here at 6,300, and the prediction of the extrapolation of the experimental data will be 6,200. So the classical simulation is about right for the total reorganization energy. Then we added 2 spectator modes, 2 ruthenium, a ruthenium-2 and a ruthenium-3 vibration. And they could be either parallel or perpendicular to the electron transfer direction. All the vibrations, they're either allowed in the infrared, parallel or perpendicular. So by doing this way, this model, we can see what they all are. And as a function of 2J on lambda, down here, going from 100th to 100, at 100th it's strongly localized, at 100 it's strongly delocalized, and see the vibrational levels here correlate across. The tunneling mode becomes the antisymmetric mode, down here. There's not a simple correlation, which you'd expect. And these fundamentals here go up and become the overtone there. So a very complex behaviour. But if you put, that's without solvent. If you put the solvent in there, this is our three-mode solvent, this is what you get. And this is a very different behaviour where there's an apparent coalescence of the localised transitions to the delocalised one across the region where 2J and lambda becomes 1. And our basic theory to explain all the data is that down here the localised region is well known, the delocalised region is well known, but in here it should be localised, but for a large region you only see it as if it's delocalised. Yeah, too low. And it's this region here, there's a double well, but the double well doesn't support zero-point vibration. So we think that's the core to understanding the experimental data. In this region here, there are solvent fluctuations. Each line here is a different vibrational level of the solvent. And they're interacting strongly with the chromophore. So the chromophore's vibrations are no longer localised, they delocalise over the whole system. And when they can't support zero-point vibration, that's when you're seeing all these inconsistent signatures, and it's all fluctuation. The solvent fluctuation is driving the phenomena and introducing apparent localisation on a picosecond time scale. And this is the last one. This is where it all falls down. This was our original time correlation function from the classical mechanics. We take our three-mode model and Fourier transform it back to see, this is the quantum model, what is the time response that comes from it? It looks nothing like the original. So our three-mode model doesn't represent the data correctly because it's not dissipating energy properly. So the self-energies are all wrong. We need something that goes well beyond what we've ever done in the past, and we've come to ICAM asking for help on how to do this different thing. So thank you very much.
Thank you. Questions?
So just to clarify, the numerical experiment was you first did it where you had the 3 plus on one side and the 2 plus on the other, got it to equilibrate and relax, then you just flipped it?
Flipped it, yeah.
That's how you got, okay.
Watch the dynamics after the flipping.
Instead of fully localized system, have you tried 2.5 system? Same empty simulation and do the same calculation to get the spectral density?
Yes.
What is the difference?
Well, it won't look anything like it. There's no dipole moment change. The solvent won't respond.
Locally, you can.
Yeah. So that's an uninteresting problem. But this problem is interesting because it tells you the parameters that go into the full quantum simulation that can handle from one extreme to the other. So it's a way of calculating the input data to the real calculation by assuming the fully localized limit. Now, you can also pull out data by assuming the fully delocalized limit. That allows you to pull out the electronic coupling J. And the two of those then combine to give the full simulation. But it's not the dynamics that you want to do in the delocalized limit. It's the electronic structure calculation to get the electronic coupling. And it's a rather huge non-quantum effect based on it.
I'd be very concerned about the dynamic in a classical simulation of a cluster of 195 water molecules, which I assume you've used a constrained model as well.
Yeah.
That's what I mean. If my question is more, are your results sensitive at all to the classical part of the calculation?
I think the details are very sensitive, but the basic picture isn't. And clearly here we have a much more serious problem than that one.
Because I mean, you'll freeze in if you take a cluster. I mean, the dynamics of the water will be terribly stressed.
Because the energy is only dissipated into 190 molecules, you end up with still a couple of kilocalories of energy. The temperature rises at the cluster whereas it shouldn't rise. There's no infinite range dissipation.
The boundary effect will be that the water is highly ordered.
Yes, the problem was I'd been doing it with analytical methods or by trying to spoof off the observed correlation functions, but they were all for a different system. The Creutz-Taube ion is really very different due to those pockets that sit in there. And right at the end I realised that it was all nonsense what I was doing before, and that this is actually very much better than trying to take anything from the literature. But that gave me 2 days to redo the entire calculation from scratch. And the only code I could get running in 2 days was Gaussian, and it didn't permit periodic boundary conditions that I found out after I'd done a lot of the work. So that's why I was done with the cluster. Not by design.
Also, just thinking of things people might do here, two nice things people might do here is do femtosecond spectroscopy on the actual
Molecule.
Creutz-Taube ion, and also then some more molecular dynamics with periodic boundary conditions or water.
The problem with that is the real Creutz-Taube ion is delocalized due to the electronic coupling, and so the actual solvent dynamics is poor. It won't show this sort of effect. So the experiment that was done by Hupp and Barbara was to take the CN in the middle, where the CN gives you huge E0 and strongly localize it on one side. So that was a model compound to get at the effects. Where here we're doing a model calculation by ignoring the terms that you referred to, which would couple the 2 electronic states during the simulation. We've chopped them off to get our data, and they used a different molecule to get the data. So it's hard to actually do it on the Creutz-Taube ion because that won't reveal the intrinsic physics which underlies the more complex scenario.
Actually, I look at this ST, there's some evidence in the literature for no matter if the price is localized, you have 5+ charge there. The water significantly slow down. If you have first shell.
So yeah.
Yeah, it's extended. There's some evidence in the literature to experiment. How you will dictate to 20%. The ST.
Yeah.
Yeah, so this is looks like a free ST, free water ST, sort of.
Yeah.
So
that's about 20 femtosecond. It's the same as the Hupp paper, is the 20 femtosecond paper.
No, if you just feed up to 1 picosecond or 1.5 picosecond.
Oh, picosecond.
Yeah, the picosecond.
Sorry.
It would give you 800 femtoseconds, something like that. Like that depends upon the window. Whatever you did the feeding.
You want to show us what you're saying? Top button.
Top button. Okay. So you feed up to here.
Yeah.
And you found that 50 femtoseconds, something like that.
Yeah, 20 femtoseconds.
So
Yeah,
if you
same as
consider
Hupp.
that, if you just feed up to here, like where, so you may
Yes.
get a decay of 800 or 700 femtoseconds, which is the measured stuff or standard dye.
Yeah.
That we measure.
Yes. Yeah, that's there too. They're both
So
there.
it
Yeah.
depends upon the window. That
Yeah.
how far you are.
even the Java sort of
Yeah.
if you have 5 charge,
Yeah.
the maximum, the first shell,
For sure. Yeah.
or maximum,
But-
much.
This
I don't
Hupp's
know-
experiment is
I don't know what's
exactly
the
that.
experiment, how
Yeah.
to make it is 20 femtosecond, maybe only initial component. But if we look at the evidence, then little people have already made it for this even 2+.
Mm.
You have 5+ field line. So that's what will be significantly slow down.
Yeah. Well, the counter ions are being ignored in this as well, and there will be counter ions with probably within that range that I've drawn there. So so there's a lot of screening associated with them with the counter ions. So it's a difficult problem.
No, in fact, I was about to ask that. What about counter ions? What counter ions are there? Yes, exactly.
Perhaps in order to resolve that issue, the three-mode model and the discrepancy between these two, some other people use a trick like 3 Brownian oscillators. Instead of just harmonic oscillator, you can add some property phase in terms of quantum which so that you can make this curve nice.
Yeah.
Maybe that's not.
Yeah, that's precisely what we need. A proper version of the self-energy to describe the interaction.
Well, you could just fit with you've got you use 3 frequencies, add in 3 damping terms for each frequency. I mean, that'll smooth it out.
Yeah. So subtle things like the period here is double the period down there. Which flows through all the standard equations in the literature. But I don't know how to deal with that. But other than that,
Yeah, just a sort of slightly off the wall question, I guess. I mean, the 2 logical modes have something which is perfectly localized 2 plus 3 plus, and then the average 2.5. But how much is it possible to have something which is 2.9 and 2. Equivalent? So
in photosynthesis, yes, that was all of what Prof. Hush was showing, and that's caused by the asymmetry of the protein field.
Yeah.
So here you've got, you have to integrate over the vibrational wave functions. You can't trace over them, as was described with the quantum coherence talk. So that will always give you numbers which can be interpreted that sort of way. But the charge isn't the thing that you don't measure the charge, you measure a vibration frequency or a spectrum or something like that. So then you're trying to interpret those observed properties in terms of the charge. But if there's something which will cause localization, then you can measure it with an ESR spectrum. So in the protein, it's the protein field, but here I guess I was saying it's these sort of vibrations here of the solvent, this long time response of the solvent that's inducing localization, and then your concept of a partial charge makes sense during the time scale of that solvent fluctuation.
If you have a partial charge, then that takes into account the vibrations of the protein center, doesn't it? And so can you kind of work backwards and say, what sort of partial charge do you need to give you that sort of vibration in the middle?
The partial charge concept is trying to trace over the vibrational motions to come up with an electronic property, and that's what you can't do in this regime. So, so the idea can be extracted as an average, but it's not like the Born-Oppenheimer theory holds, where that's all you need, which is what classic organic chemistry operates in. So it's. I know what you're trying to say. We do it all the time too, but not here because there's no Born-Oppenheimer. But it's intrinsically more complex than you could get out of that sort of analysis.
But that could come back to where your counter ions are versus where the water molecules are. So, for example, if